Hi. So, batteries not included. It's a common phrase that you might find with consumer electronics, but it'd be really weird if that same thing applied to our electric vehicles, right? But it's nearly the case. So first, let's have a little look at these batteries. You've seen cylindrical and pouch cells in the talk just now, and you've used devices like mobile phones, laptops. But if you've been in a vehicle like a Tesla, that uses cylindrical cells. Or if you've been in a Jaguar I-Pace or a Nissan Leaf, that uses pouch cells. Now in a vehicle, we take lots of these cells in conjunction to make modules, and lots of these modules to make the pack. And we combine these cells in series and parallel. When we combine them in series, we up the voltage, which means you can go faster. When we combine them in parallel, that ups the capacity, which means you can go further. And just like vehicles on the road, these packs come in all different shapes and sizes. Some go in the boot of your car, some go in the floor or under the seats. So if you're sitting there thinking that you want to make some electric vehicles, you're going to need to get your hands on some of these cells to make modules, to make packs. But I've got a bit of bad news for you. You'd have to look outside the UK and even outside Europe to get your hands on these. So it means you have to fly them in or ship them in, thus creating even more emissions before you've even put an electric vehicle on the road, which kind of defeats the purpose, right? And some of you might be thinking, electric vehicles don't seem that useful then. Some of you might be thinking, what about all the extra electricity that we need to generate to charge these cars? Or some of you might just be thinking, here we go with the electric vehicles again. But more and more we're hearing about the climate crisis, and rightfully so. So it's important not just to electrify our cars, but as Anisha said, to electrify the entire transport system. So I'm a car fanatic, so I'm going to stick with cars for just a moment. And this is the first one I'm going to talk about. This is called the Hellyer, and it was made by Cambridge University's Eco Racing team. And they built this for an endurance challenge to go from the north of Australia to the south of Australia. Now that's about 3,000 kilometres or 1,800 miles. And to put that in context, that's like driving from Coventry to London 17 times. And they had to do that in 6 days. And they had to do that without charging for the first 1,200 kilometres, nearly half the race. But the technology behind this is really, really clever. They managed to get to 50 miles an hour on the same amount of power it takes to boil a kettle. And they managed to travel 900 kilometres without charging, which is like doing a trip from London to Edinburgh. And this is the other end of the scale. This is the Hypercar from Ariel, which is the same company that brought you the race car that looks like it's made out of scaffolding on the sides. This is actually a hybrid, but the battery is still the main source of power. And this is capable of getting to 100 miles an hour in 3.8 seconds and generates 1,180 brake horsepower. So keep these two cars in mind. So back to batteries. How are we going to make the volumes that we're going to need in the future? Well, for that we have the AMPLIFII project. That stands for Automated Module to Pack Pilot Line for Industrial Innovation, which I know is very catchy. I sing it home all the time. And I think our logo would look great on a t-shirt. So on AMPLIFII, we take cylindrical cells like this, and we make modules like this. But it's all well and good just going and making a load of modules. How do we make sure that we make them smarter so that we reduce our consumption and boost our output? For that, we turn to automation. And when I say automation, I mean the robots and the data behind them. So this is our first robot. It's called the cell loading system. It tests and picks cells, so we know that we're making really good quality modules. It tests the cells for their voltage and resistance, and then picks and places those cells into the right positions in the right orientation. And that orientation is really important for those series and parallel connections that I mentioned. Another bonus is that it's a lot faster than a human like me sitting at a bench counting out 150 and placing them the right way up. So once it's finished in the cell loading system, it goes and gets the rest of assembly steps finished. And then we move on to welding. So this is how we make those series and parallel connections. So just like your AA battery in your TV remote with those two springs holding it in, that makes the connection. So we have lots of different welding technologies to make those connections. Up here on the left, you see wire bonding, which is just attaching a wire to the top of the cell to the rest of the battery. And on the right, you have ribbon bonding, which is a thin strip of metal that's joined at both ends. And again, for this, we use a robot. It's far more accurate, it's faster, and it means that I don't have to sit there worrying about making 300 welds and potentially getting one wrong and binning an entire module. Then we have Pulsar Welding, which is on the left, and laser welding, which is on the right. Laser welding is really, really fast and is a potential technology to get the volumes of batteries that we need in the UK. Now, Pulsar welding is slower, but it's a proven technology, and we can get loads of data out of it, which means we know that we're going to make a good weld every single time. And that's really important because we don't want to over-weld and potentially puncture the cell, or under-weld and not connect the cell at all, because otherwise that cell's sitting in that module not doing anything, and we want to harness the full electrical potential of that module. So this is what we're doing on AMPLIFII, but it's just a stepping stone. It's a small lab, and we can only make small batches. And you remember those two cars that I showed you earlier? Well, the AMPLIFII project has made batteries for both of those vehicles, but it's just 2 cars. So we need to go a lot bigger. And this is where the UK Battery Industrialisation Centre comes in, or UK BIC. Their goal is to build a flexible line that can make lots of different types of cells, modules, and packs, and develop the skills that we need in the UK. In AMPLIFII, we can make a pack in a couple of weeks. But at UK BIC, their goal is to make 2 packs in 8 hours. So things look good for batteries, right? We're going to get the volumes that we need, and we're going to get the skills that we need. Sounds good. We've grounded some planes and anchored some ships, so we've made the air a bit greener in the process. But we're not quite done. We're not done getting manufacturing to the volumes that we need. We need gigafactories like Tesla has. We're not done researching the materials that we need or how we get them, so we reduce our damage on the environment. We're not done building the robots or analysing the data so that we know we can make higher quality batteries. And some of these things don't just apply to batteries, they apply to all the different products, services and tools that you use on a daily basis. So this is where you come in. We need people from loads of different skills and backgrounds to help us and carry on the research that we've done, run the machines and maintain what we're putting in place today. So if you get involved in a small way or take a career path in STEM, you'll be helping to improve the world that you're about to inherit and the lives of the people in it in ways that you might be about to invent. Thank you.